A stone wall can be a locked book written in a forgotten language. These ancient structures, from the Cyclopean fortresses of Greece to the interlocking puzzles of the Andes, are not silent ruins. They are a sophisticated engineering language, a global code carved in granite and limestone that speaks of physics, society, and a deep desire to endure. By the end of our journey, you will gain the ability to read these walls yourself, to see the deliberate genius in every seemingly impossible joint. How did cultures separated by oceans and develop the same silent syntax for building? What profound message about human ingenuity is cemented into stone blocks that have outlasted empires? When you look at an ancient wall, what do you believe it was truly built to say that language begins with a single, powerful rule of grammar, the principle of compressive strength? Think of stone not as a solid, unyielding mass, but as a community of microscopic crystals all huddled together, bearing weight. When force pushes straight down on them, they are incredibly strong, supporting immense loads for centuries. This is the foundational verb of ancient engineering, to compress. But introduce a sideways push, a shear force, and those same crystals can be apart. Every ancient builder understood this instinctively. They weren't just stacking rocks, they were directing traffic, ensuring that the immense weight of a wall, a pyramid, or an arch traveled in a straight, vertical line down through the heart of each stone. This is why the colossal blocks at sites like in Peru or the foundations of Mycenae in Greece are so often trapezoidal, wider at the bottom. The shape itself is a grammatical sentence. It says, channel the weight here, keep it centered, keep it true. The stone's own immense mass becomes its greatest source of stability, locked in place by gravity. This leads to the second critical rule, the art of the joint. In a mortared wall, the adhesive does much of the work. But in the oldest, most enduring megalithic work, the joint itself is the technology. The goal was to create a connection so precise that the surfaces mate completely, maximizing friction and distributing load across the entire face. This practice has a name, the geometric art of cutting three-dimensional solids to fit together. It transforms construction into a three-dimensional puzzle where every block is a unique piece. The famous polygonal walls of the Inca are in this, each irregular block carefully shaped to interlock with its neighbors on multiple planes. A force hitting one stone is immediately transferred to several others around it, a distributed network of strength. This interlocking grammar provided a brilliant solution to another ancient challenge, seismic activity. In an earthquake, a rigid wall built with mortar can crack and collapse, but a well-fitted dry stone wall with interlocking blocks can actually sway and settle, the stones dancing slightly in their carefully crafted seats before settling back into place. The joints are not a weakness, they are designed shock absorbers. So when you see a wall without mortar that has stood for 1,000 years, you are not looking at primitive simplicity. You are reading a sophisticated paragraph written in the dialect of friction, geometry, and dynamic response. It is a testament to a profound observation that the most permanent bonds are sometimes formed not by glue, but by perfect, mutual fit. This grammatical foundation raises a compelling question. If these principles are so universal, how did the very first builders stumble upon them? What were humanity's earliest experiments in writing this enduring language of stone? Gravity was the first teacher, and its lesson was simple and profound. Every ancient builder began their education by watching a stone fall, by feeling the unrelenting pull of the earth. Long before complex machinery, this invisible force was the primary architect, the silent partner in every construction project. The most fundamental rule written into those old stones is a direct dialogue with this constant pull. It is why you will almost never find an ancient wall that is perfectly vertical from top to bottom. Look closely, and you will see a subtle, deliberate slope. The base is always thicker, and each layer of stone steps slightly inward as it rises. Builders call this technique battering, and it is not an aesthetic choice. It is a structural poem. It ensures that the center of gravity for the entire wall falls well within its own footprint, creating a wide, stable stance against the wind and time. The wall is essentially leaning into itself, using its own immense weight to achieve balance. This is the engineering language's most basic and powerful verb, to settle. It is the art of allowing gravity to do the work of locking everything in place. We see this principle elevated to an art form in some of the most iconic ancient structures. Consider the massive lintels atop the standing stones at Stonehenge. Those horizontal slabs are not merely resting there, they are carefully engaged in a gravitational conversation. Their tremendous weight pushes down on the uprights, increasing the friction at the contact points and making the entire assembly more rigid. Or look to the beehive-shaped tombs of ancient Mycenae, built with corbelled arches. This technique involves stacking rings of stone, each one cantilevered slightly inward over the one below until they meet at the top. There is no keystone, no mortar, just a perfect balance of opposing forces. Each stone is held in a state of perpetual compression, pushing against its neighbors, with gravity acting as the eternal glue. The entire structure is a monument to directed weight. This creates a fascinating paradox. These monuments, which seem so solid and immovable, are actually in a constant, dynamic relationship with the planet itself. Their stability is not a static condition, but an active achievement. They have withstood not by defying natural forces, but by channeling them, by turning the Earth's own pull into the foundation of their permanence. It is a testament to a deep, almost intuitive understanding of physics, a dialogue written in granite and limestone. And to engage in this dialogue so masterfully required more than just an understanding of forces. It demanded a profound intimacy with the very substance they were shaping. The builder had to know stone not as a dead thing, but as a material with its own personality, its own grain and secrets. To truly speak the language of stone, you first had to learn how to listen to it. Before a single block was set into a wall, the ancient engineer engaged in a deep, almost intimate dialogue with the material itself. This was not a brute force operation, it was a careful reading. Every stone has a story written in its grain, a personality defined by how it formed under immense heat and pressure over eons. The second principle of this engineering language is material intelligence, the ability to hear that story and work with it, not against it. A master builder was first and foremost a practical geologist. They would examine a raw outcrop, running their hands over its surface to feel its texture, tapping it to hear its resonance. They were searching for clues, the natural cleavage planes where the stone was predisposed to split, the direction of its crystalline grain that would determine its strength. They understood that stone is not a uniform substance, it has a memory and a will. This profound knowledge directly dictated their choices. For the massive foundations of a temple or a fortress wall, they sought out igneous rocks like granite or basalt, born from fire and cooled slowly deep within the earth. These materials possess an incredible compressive strength, an ability to bear unimaginable weight for century after century. They became the unwavering consonants of a structural sentence. For the finer work, for the decorative friezes or the intricate statues that would adorn a building's face, they turned to softer, more malleable stones like limestone or sandstone. These were the vowels, capable of being shaped into flowing curves and detailed narratives. This intelligence extended brilliantly into the very act of liberation, the quarrying process. To modern eyes, the idea of cutting ton blocks from a mountainside with only bronze or stone tools seems impossible. But they didn't fight the stone, they convinced it. One of the most widespread techniques was a beautiful manipulation of physics. Workers would build a small fire directly against the rock face, heating it intensely. Then they would douse the hot stone with cold water. The sudden thermal shock would create micro-fractures, weakening the stone along a desired line. Into these tiny cracks, they would drive dry wooden wedges. Then, they would pour water over the wood. As the wedges absorbed the moisture, they swelled with tremendous, gentle force, patiently persuading the stone to fracture cleanly along its own natural plane. It was a linguistic act, using the stone's own properties, its response to heat and its inherent weaknesses to articulate a perfect block. This was not extraction, it was a conversation. The stone participated in its own shaping, guiding the builder's hand. This respectful collaboration dramatically reduced the sheer labor required, but more importantly, it resulted in a block that was fundamentally sound, already oriented to best handle stress. By honoring the material's inherent story, the builder ensured the final wall would tell a story of permanence. And once these intelligently harvested blocks were ready, the most visually stunning grammar of all could begin, the creation of joints so precise they seemed to defy the very idea of separate pieces. The space between stones is where the language finds its voice. In a mortared wall, the gap is filled, silenced. But in the oldest traditions, the joint itself is the eloquent punctuation, a carefully crafted interface that tells a story of foresight and physics. The most visually arresting example of this is the polygonal joint, a masterpiece of interlocking geometry seen in the walls of, or the sunken ruins of in Greece. To the untrained eye, it looks like a chaotic stone puzzle, a jumble of irregular shapes somehow fused together. But this is not artistic randomness, it is deliberate engineering poetry. Each face of each block was painstakingly dressed, shaped over countless hours, to create not one, but multiple planes of contact with its neighbors. This technique, which modern structural engineers call asperity interlock, transforms a simple stack into a three-dimensional network. The load from above is never borne by a single point. It is distributed across a wide, complex landscape of interlocking surfaces. This design carries a brilliant secondary benefit: seismic intelligence. When the ground shakes, a rigid, mortared wall tries to resist the movement and can crack under the strain. But a well-fitted polygonal wall is designed to flex. Those intricate joints allow for tiny, controlled movements, the stones shifting minutely in their custom-fashioned seats, absorbing and dissipating the energy before settling back into place. The wall breathes with the earth it dances, and in dancing it survives. This explains the legendary precision so often described, the fact that a knife blade cannot be inserted between the stones. That tightness was not primarily for visual perfection, it was a functional imperative. By eliminating any gap, the builders maximized the surface area contact, and therefore the friction between blocks. More crucially, they eradicated point loads, those dangerous concentrations of stress that can cause a stone's face to chip or flake away over centuries, a process called spalling. A perfect joint ensures the pressure flows evenly, like water across a flat stone, preserving the integrity of each block. This art of the joint transformed a collection of individual rocks into something new, a monolithic yet flexible entity, a single resilient skin woven from stone. To achieve such a transformation, to choreograph this dance of polygons, required more than skilled hands. It demanded a hidden framework of thought, a silent mathematics guiding every cut and placement. That perfect fit was not born from guesswork, but from a silent mathematics. Behind every seemingly irregular stone in those ancient walls lies a hidden framework of geometry, a set of proportional rules as rigid and purposeful as the syntax of a sentence. This mathematical backbone was the invisible grid upon which the entire engineering language was written. It transformed intuition into a repeatable, scalable science. Builders across the world tapped into universal constants, like the golden ratio, a proportion found in nature from seashells to spiral galaxies, which they incorporated into dimensions to create structures that felt inherently balanced and harmonious to the human eye. They employed Pythagorean triples, sets of three whole numbers that perfectly describe a right-angled triangle, to ensure corners were perfectly square, as seen in the flawless 90-degree angles of the basalt blocks in Egypt. Even the celestial dance overhead provided a template, with walls and doorways aligned to solstice sunrises or specific stars, anchoring earthly construction to the cosmic order. These systems were far more than symbolic gestures, they were functional algorithms for stability. The trapezoidal shape so beloved by Inca architects is a geometric equation for seismic resilience, its sloping sides naturally directing weight inward toward a wider, more stable base. To execute this precise grammar across vast projects, builders developed ingenious portable toolkits. They used knotted ropes, called surveyor's cords, which could be stretched into triangles to check for square. They employed simple wooden pegs and string to scribe perfect circles or lay out complex angles on the ground before a single stone was cut. Crucially, they standardized their measurements, using units like the Egyptian cush or the Andean, a personal measure based on a man's forearm. This meant that a master architect in the capital could design a temple, and a team of builders 100 miles away could replicate it perfectly because they were all reading from the same mathematical script. This shared syntax allowed for the breathtaking scaling of designs, from an intimate shrine to the colossal, terraced walls of an entire mountain city. The geometry was the shared vocabulary that made such monumental conversation possible. With this precise mathematical blueprint held firmly in mind, the next step was to translate those perfect angles and proportions from thought into solid rock, a task that demanded tools of elegant simplicity and immense power. The grammar and mathematics of stone required physical articulation. To write this enduring language, ancient builders wielded a limited but profoundly powerful vocabulary of tools, the simple machines. The lever, the inclined plane, the roller, and the wedge were not just implements. They were the active verbs of construction, transforming abstract principles of physics into tangible, monumental reality. Consider the most iconic challenge, lifting a stone block weighing as much as several elephants to a height of hundreds of feet. The solution was linguistic in its elegance: turn a vertical lift into a horizontal journey. The earthen ramp, a massive inclined plane built from rubble and packed earth, is the most famous hypothesis for the construction of the Great Pyramid. It transformed an impossible direct hoist into a gradual, manageable incline, where teams could pull a sledge-mounted block upward with a sustained, collective effort. This was not brute force. It was the strategic application of a fundamental law, reducing the required effort by increasing the distance over which it was applied. Once a block reached its general level, finer positioning was achieved with levers and counterweights. A long timber placed under a stone's edge, with a smaller rock as a fulcrum, could amplify a worker's strength 100-fold, allowing for minute adjustments, nudging a ton block into its perfect weighting socket with the precision of a scribe placing a final character on a page. The tools themselves left their own stories etched into the stone. The parallel striations on a granite surface in Egypt speak of relentless sawing with a copper blade and an abrasive sand slurry. The pockmarked faces of Andean stones reveal the patient pecking of a stone hammer, slowly dressing a surface by crushing its crystalline grains. Each mark is a testament to incremental progress, to a patience we can scarcely comprehend today. These tools were direct extensions of the builder's embodied knowledge, the physical means to speak the language of mass and movement into silent, permanent form. The staggering efficiency of this simple toolkit is only revealed when we step back and witness the staggering scale of the sentences they wrote, moving from the quiet theory of physics to the roaring, monumental practice of empires. The language of stone found one of its most dramatic accents in the citadel of Mycenae. Here, the syntax of power was carved directly into the landscape. Around 1350 before the Common Era, builders assembled walls from colossal, jagged blocks of local limestone, some weighing more than 20 tons. They did not seek perfect polygons here, but a different kind of expression. The technique is known as Cyclopean masonry, a name born from the awe of later generations who could not believe human hands were capable of such work. The historian, upon first uncovering these ruins, famously declared that only the mythical one-eyed giants could have moved stones of such scale. The name stuck, a testament to the intimidating dialogue these walls were meant to have with any who approached. But this was not the work of giants, it was the work of brilliant engineers speaking a deliberate dialect. The principle at work is gravity packing. Each enormous boulder was selected and positioned so its immense mass and rough, interlocking faces created tremendous friction with its neighbors. The builders then skillfully chinked the inevitable gaps with smaller, wedge-shaped stones, effectively locking the larger blocks in place. This created a rigid matrix, a wall that could flex and settle without a catastrophic failure of its overall structure. The very irregularity of the shapes contributed to seismic resilience, as the blocks could shift and grind against each other during a tremor, absorbing energy before settling back into a stable configuration. The language spoken here is one of raw, imposing permanence. Every uneven surface, every shadowed crevice between the monstrous stones was designed to overwhelm. It communicated the absolute authority and defensive might of the Mycenaean kings, a message carved in limestone that any potential foe would understand instantly upon sight. This was engineering in the service of symbolism, where the structural grammar also served as a psychological barrier. From this vocabulary of intimidation in the Aegean, we can journey across the world to hear a remarkably similar language spoken in a completely different tone, one of elegant, seamless integration with the living earth. The language spoken at is a dialect of exquisite precision. Where Mycenae shouted with raw, imposing mass, the Inca fortress above whispers with the quiet confidence of a perfect equation. Its walls, built from diorite and andesite, are composed of polygonal blocks so meticulously fitted that the joints appear as fine, dark lines drawn on stone, not gaps carved between them. Some of these stones boast 12 or more angles and sides, a geometric puzzle of staggering complexity. This is not mere artistry. It is a highly evolved grammar designed for one of the planet's most active seismic zones. The entire structure is engineered to move. The walls have a pronounced inward tilt, a batter that directs weight toward a wider, more stable base. Each interlocking block, with its multiple contact planes, is a custom-shaped gear in a vast, stone machine. The genius is often found in the smallest details, like the subtle L-shaped keystones strategically placed within the walls. These stones act like three-dimensional locks, preventing any section from sliding outward during the violent shaking of an earthquake. The wall was designed not to rigidly resist the Earth's movement, but to sway with it, to dance in its carefully crafted seat, and then settle perfectly back into place once the tremor passed. Achieving this level of symbiotic precision required a patient, almost meditative construction method. Historians and stonemasons theorize a process called scribed fitting. A roughly shaped block would be painstakingly maneuvered above its destined neighbor and lowered onto it. The points of contact, the high spots, would be marked. The block would then be hoisted away, and those marked areas would be ground down, often using nothing more than harder stones and abrasive sand. This cycle of lower, mark, and grind would be repeated dozens, perhaps hundreds of times, in a slow, iterative conversation between mason and material. It was a dialogue of millimeters, a testament to a worldview that saw time not as a commodity to be spent, but as a foundation to be built upon. The result is a wall that has endured over 5 centuries of violent upheavals, not by fighting nature, but by listening to it and responding in a language of perfect mutual fit. This raises a profound and haunting question that echoes across the continents, from Greece to Peru. How did cultures separated by immense oceans and thousands of years develop engineering languages that speak so many of the same core principles? These parallel discoveries across the globe form one of history's most compelling silent conversations. From the cloud-ringed fortresses of the Andes to the sacred platforms of ancient Italy and the fortified slopes of Japan, we find the same answer written in stone, yet there was no shared blueprint, no wandering master mason who taught the world. This is the independent invention paradox, and it whispers something profound about human ingenuity itself. When cultures as distant as the Inca, the pre-Roman peoples of, and the builders of castle in Japan all arrived at polygonal, mortarless walls, they were not copying each other, They were independently arriving at the same grammatical rules in the universal language of physics. They were solving the same equation, with gravity and seismic force as the constants. The necessity of creating something permanent from a brittle material, using only human labor and simple tools, funnels the mind toward a specific set of logical conclusions. A wall must be stable, so you give it a sloping batter to direct its weight inward. The ground shakes, so you interlock the pieces to allow them to flex as one. The joints are the weakest point, so you make them perfect, maximizing friction. It is a convergent evolution of technology, much like how wings evolved separately in birds, bats, and insects. The environment presents the problem, and the human mind, equipped with observation and trial, iterates toward an optimal solution. Scholars like Jared Diamond have explored this concept as environmental determinism, where landscape and challenge powerfully shape the path of innovation. A mountain people everywhere will eventually master terracing, a river people will develop irrigation, and those living on volatile fault lines will inevitably discover the seismic wisdom of the interlocking joint. This paradox dissolves the mystery of contact and replaces it with a more awe-inspiring truth. It reveals a shared cognitive toolkit buried deep within our species. It suggests that the drive to build permanently and the logical pathways to achieve it are a fundamental part of the human story. But if the engineering grammar is a universal response to physical laws, then the specific dialect, the style and symbolism infused into these walls, must be where culture speaks its unique name. The how may be a global conversation, but the why, the message cemented into these stones, is a deeply local story. What were these impeccable walls truly built to say beyond just standing strong? A wall is never just a barrier, it is a statement. The engineering language we have been deciphering possesses a powerful semantic layer, a vocabulary of meaning that communicated status, belief, and identity to everyone who saw it. The choice of dialect was a profound cultural declaration. Consider the contrast between a wall of finely dressed ashlar blocks, each one a perfect, smooth rectangle, and one of rough, chaotic Cyclopean boulders. Both are structurally sound, but they speak entirely different social languages. The ashlar wall, like those gracing the later temples of Egypt or the forums of Rome, is a monument to centralized, hierarchical power. Its perfection requires immense, coordinated labor, specialized craftsmen, and a commanding authority to direct it all. It says, we have mastered nature so completely we can reduce the mountain itself to obedient geometry, and this order reflects the divine right of the ruler. It speaks of a god-like permanence etched into the cityscape. Conversely, the robust, interlocking polygonal walls found in many earlier Mediterranean societies might tell a different story. Their strength comes from collective adaptation, from fitting diverse pieces into a resilient whole. This engineering dialect could reflect a more clan-based or federated social structure, where resilience emerged from cooperation rather than top-down command. The wall itself becomes a metaphor for the community it protects, each uniquely shaped stone essential to the integrity of the whole. Beyond social structure, these walls were often cosmological maps. Their precise alignments to solstice sunrises, like the famous stone at or to specific stars, embedded vital astronomical knowledge directly into the urban fabric. The wall was not just facing a direction, it was conversing with the heavens, anchoring the community to the cycles of the cosmos and the favor of the gods. Thus, every technical decision carried symbolic weight. The intimidating, irregular Cyclopean style was a grammar of fear and might, designed to overwhelm an approaching enemy. The seamless, perfect joints of Inca masonry were a dialect of harmony, expressing a worldview that sought seamless integration with the living earth. The choice to leave a surface rough or polish it mirror smooth, to use local stone or import rare marble from across an empire, these were all conscious sentences in a long cultural narrative. This symbolic function reveals that building such monuments required far more than just skilled masons. It required an entire society acting as authors. The laborer quarrying the stone, the priest defining the sacred alignment, the ruler commissioning the work, and the farmer who fed them all were all participating in writing this permanent statement into the land. The wall was their collective voice, frozen in time, telling us not only how they built, but more importantly, who they believed they were and what they held sacred. The voices behind this silent language were not anonymous laborers, but master linguists of stone. To label them as primitive is to misread the text entirely. These were highly specialized professionals, the original civil engineers, whose deep understanding of statics, material science, and logistics was earned through generations of applied wisdom. In ancient Egypt, the builders of the royal tombs lived in a privileged, planned community like El Medina, a state-supported settlement of artists, scribes, and master masons. They were a revered class, with their own guilds and a social standing that reflected the sacred importance of their craft. Their work was not brute force, it was a sacred dialogue with eternity, and their skill granted them a status far above that of a common field worker. Across the ocean in the Inca Empire, the state harnessed this expertise through a system called a form of rotational labor service. But this was not mere drudgery. They would draft skilled stonemasons from across the realm, bringing them to work on imperial projects this system acted as a powerful engine for knowledge transfer, a way to disseminate the latest dialect of engineering grammar across a vast and mountainous empire. A mason would work alongside a mason from the sacred valley, sharing techniques and solutions, and then take that refined knowledge back to his home province. This was a continuous, living conversation that elevated the entire empire's architectural language. These builders operated without formal textbooks, yet their empirical knowledge was vast. They understood that a stone's strength varied with its grain, that a wall's stability depended on a precise center of gravity, and that managing a workforce of thousands to quarry, transport, and fit blocks was an epic feat of logistics and morale. They combined this inherited knowledge with relentless on-site innovation, constantly adapting their grammar to the unique challenges of each site, each stone, each seismic rumble. Their legacy is the wall itself, a silent testimony written not by slaves, but by the most fluent speakers their civilization could produce. This profound skill, however, immediately confronts us with a staggering logistical puzzle. How did these linguistic masters, without cranes or engines, physically pronounce these stone sentences across miles of impossible terrain? The most fluent sentence is useless if you cannot move the words into place. The true syntax of this ancient engineering language, the grammar that gave order to chaos, was logistics. Before a single stone could speak of physics or culture, it had to be persuaded to travel. Consider the scale of this silent conversation. At Baalbek in modern-day Lebanon, a foundation stone known as the Stone of the Pregnant Woman weighs an almost incomprehensible 800 tons. In the Peruvian highlands Rose rhyolite blocks weighing 70 tons each were from a mountainside across a valley and a raging river from their final resting place. Moving these megaliths was not an act of brute force, it was a masterpiece of social choreography, a ballet performed with ropes, levers, and human rhythm. The theories of transport read like a manual of elegant physics. For the stones of Egypt, the most likely method involved wooden sledges gliding over tracks lubricated with water or clay slurry, turning bone-jarring friction into a manageable, consistent drag. Teams of workers, coordinated by rhythmic chants or drum beats, would pull in unison, transforming individual effort into a single, flowing force. In the Andes, where the terrain sledges, builders may have used a system of earthen ramps and precisely placed cobblestones as permanent rollers, inching blocks forward with levers in a patient, rocking gait. For longer journeys, like the transport of the famous Stone of the 12 Angles to river transport on enormous reed boats was likely the silent highway. Each method was a dialect of movement, a specific way of asking the stone to journey. But the stone's journey was only one thread in a vast tapestry of planning. This logistical framework was the invisible sentence structure of an entire civilization. To feed, house, and equip the army of workers required for a decades-long project demanded a command hierarchy as sophisticated as any modern corporation. It required foremen who could translate an architect's vision into daily tasks, quartermasters who allocated tools and food, and scribes who tracked progress and resources. The quarry was a factory, the transport route a supply line, and the building site a carefully staged assembly point. This level of organization reveals that these societies possessed not just engineering genius, but a profound capacity for long-term collective action. They were building a legacy, and they understood that such permanence required a foundation of meticulous, sustained cooperation. This grand logistical conversation, however, was always conducted with a volatile partner, the living Earth itself. The most brilliant transport plan, the most perfect joint, meant nothing if the ground could shrug and shatter it all. This ultimate challenge forced the ancient linguists of stone to develop their most brilliant innovations, a seismic grammar written directly into the walls. The Earth's restless shifting demanded a new dialect, a seismic grammar. In the world's great tectonic zones, the engineering language evolved a specialized vocabulary for movement, where the goal was not to resist the Earth's convulsions, but to converse with them. This is the principle of intelligent flexibility, and its syntax is written in the very angles of the stone. Look at the iconic trapezoidal shape of an Inca doorway or window. That narrowing toward the top is not merely an aesthetic signature, it is a seismic sentence. The shape eliminates 90-degree corners, which are natural points of stress, concentration, and cracking. Instead, the sloping sides guide the forces of a tremor downward and inward, channeling the energy through the structure's wider base, where it can be safely dissipated into the ground. The entire wall often leans inward as well, a batter that further directs weight toward a center of gravity deeply nestled within the footprint. But the true genius of this dialect lies in the joints themselves. In a mortared wall, rigidity is the enemy during an earthquake. The brittle adhesive can crack, and once it fails, the whole assembly can crumble. In a dry stone wall, however, those meticulously fitted joints become controlled hinges. They allow for minute rocking movements. During a tremor, the stones can shift and grind against each other, absorbing the seismic energy as friction and sound before settling back, often perfectly into place. The wall dances in its carefully crafted seat, and in dancing, it survives. Modern structural engineers recognize this ancient wisdom as a precursor to base isolation, a contemporary technique where a building is deliberately decoupled from the shaking ground by flexible bearings or pads. The ancient builders achieved a similar effect using stone alone, creating a distributed, flexible network rather than a single, rigid monolith. Sites like the Hittite capital of Turkey, with its Cyclopean walls that have shrugged off of quakes, or the ancient stone temples of Kashmir, built in one of the world's most seismically active regions, are fluent testaments to this dynamic dialect. They teach us that true stability in a volatile world is not about absolute stillness, but about resilience, about designing structures with the grace to move and the strength to return. This profound understanding of dynamic loads represents perhaps the highest form of engineering intuition, a dialogue with invisible forces. Yet this sophisticated language, born of necessity and deep observation, found some of its most refined and silent expressions not in the citadels of the living, but in the eternal houses prepared for those who had passed. The tomb is where the engineering language whispers its most sacred dialect. In these houses built for eternity, the grammar of stone transcends the practical needs of the living and enters the realm of cosmology. Here, the precise joint and the balanced arch were not merely for stability, they were theological statements, physical prayers for permanence carved in rock. Consider the soaring interior of the so-called treasury of Atreus at Mycenae. Its beehive-shaped chamber is not a true dome, but a corbelled vault, a masterpiece of directed weight. Each ring of stone was laid perfectly level, then cantilevered slightly inward over the one below. This continued, circle upon diminishing circle, until the final capstone could close the opening at the top. There is no adhesive, no supporting framework left behind, just a perfect, self-sustaining balance of opposing forces. The entire structure is a monument to compression, a gravity-defying sentence that declares its occupant's legacy will never collapse. This same dialect of eternal security speaks from the depths of the pyramid of At Giza. Within the king's burial chamber rests a sarcophagus of flawless red granite. Its surfaces are polished to a sheen, and its lid was once fitted with a precision that aimed to hermetically seal the contents from the ravages of time and intrusion. The stone itself, chosen for its hardness and durability, becomes a perfect, undisturbed vessel. In these contexts, the technical mastery of the mason served a transcendent purpose. The seamless joint was more than a feat of engineering, it was a metaphysical seal. The perfect balance of the corbelled vault was not just structural, it was symbolic of an unbroken cycle, a soul's intended journey from this world to the next. The architecture blurs irrevocably into cosmology, the wall becoming a boundary not just between inside and outside, but between the temporal and the eternal. This ancient pursuit of an unshakable, permanent record in stone now confronts our modern world with a profound and delicate question. We possess tools that can scan, map, and analyze these structures with incredible detail. But how do we responsibly converse with these ancient texts? Our technology allows us to listen to their secrets with unprecedented clarity, but it also forces us to ask what our role should be as readers of this silent, sacred language. The silent grammar of ancient walls now finds its voice through modern technology. Archaeologists and structural engineers have become the linguists, learning to converse with these stone texts using tools the original builders could never have dreamed of. Three-dimensional laser scanners and photogrammetry create hyper-precise digital twins of entire sites, from the sun-baked stones of Karnak to the mist-shrouded terraces of. These are not simple photographs. They are immersive, measurable records where every joint, every subtle curvature can be examined to an accuracy of less than a millimeter. This allows researchers to perform a kind of digital archaeology, peeling back layers of time without touching a single stone. They use sophisticated software to run simulations called finite element analysis, which models how stress flows through a structure during an earthquake or under centuries of accumulated load. It is a way of asking the ancient wall a direct question: how do you handle this force? And listening to its digital echo for an answer. This interdisciplinary dialogue between the shovel and the supercomputer is revealing astonishing new chapters in the old story. At sites like the Pyramid of Khufu, scans have detected subtle, intentional irregularities in the core masonry, suggesting the builders were making real-time corrections as they worked, compensating for settling or material inconsistencies with a practiced eye. They were not following a rigid, unchangeable blueprint, but engaging in a continuous, responsive dialogue with their own creation. We are learning that their planning was both meticulous and profoundly adaptable. This modern decoding often humbles our earlier assumptions. For generations, scholars theorized that the immense stones of places like Baalbek were moved on simple log rollers, a theory that seemed logical to the industrial age mind. But advanced soil analysis and engineering models now suggest some stones may have been rocked and levered across a prepared bed of small, round cobblestones, a far more controlled and efficient method for mountainous terrain. In essence, we are discovering that our ancestors' empirical knowledge, born from generations of hands on trial, was in many respects superior to the conjectures of early modern archaeology. We are becoming fluent in their language not to replicate their monuments, but to preserve them and to finally comprehend the full depth of their silent, stone-born conversation. This newfound fluency compels us to ask a more urgent question: what happens when this ancient language is threatened with permanent silence, Not by time, but by our own modern world, the most fluent language can fall silent if no one is left to speak it. Our journey through the grammar of stone leads to a haunting and inevitable question. Why did we forget how to read it? This was not a simple case of abandoning an old tool for a new one. It was a profound shift in the very syntax of civilization, a change in how humanity chose to converse with the material world. The rise of new technologies offered a different kind of eloquence. The Roman development of concrete, a fluid stone that could be poured into any shape, created a faster, more flexible grammatical system. It allowed for the soaring domes of the Pantheon and vast networks of aqueducts, prioritizing volume and speed of construction over the patient, iterative dialogue of stone fitting. Later, the medieval invention of the pointed arch and the flying buttress wrote a new poetry in stone, one that reached for the heavens with skeletal grace, redistributing weight in ways that made colossal stained glass windows possible. These were brilliant innovations, but they operated on a different set of linguistic rules. They favored prefabrication and rapid assembly over the custom craftsmanship of each unique block. The economic and social equations changed, too. Empires and growing cities demanded rapid expansion, housing for booming populations, and infrastructure to support commerce. The decades-long project to build a single, perfect wall became a luxury few societies could afford. The knowledge itself, often held within closed guilds and transmitted orally from master to apprentice, was fragile. It lived in the hands and eyes of the craftsmen, not in widely circulated textbooks. A single period of profound social collapse, a conquest that dismantled the old order, could sever that chain of transmission forever. The aftermath of the Spanish conquest in the Andes is a poignant example, where the intricate seismic grammar of Inca masonry was no longer a state priority, and the master masons, their guilds dissolved, took their secrets with them. In parts of Europe following the fall of Rome, the so-called Dark Ages saw a reversion to simpler, rougher techniques, not because people became less intelligent, but because the complex social and economic structures that supported that high craft had temporarily fragmented. This loss teaches us a humbling lesson about progress. It is not a straight, ever upward line. Advanced knowledge is not a permanent possession. It is a living tradition that requires a society willing to sustain it. When the costs in time and social organization outweigh the perceived benefits, that knowledge can become obsolete, fading into silence. And in that silence, something fascinating happens. We who have forgotten the language invent stories to explain what we can no longer comprehend. We look at the Cyclopean walls of Mycenae and whisper of one-eyed giants. We gaze upon the polygonal puzzles of Peru and speculate about lost civilizations or ancient high technology. The myths we create are a testament to the awe these structures still inspire, and a confession that we have lost the vocabulary to explain them rationally. They become monuments not only to their builders, but to our own collective amnesia. Myth is the echo of a forgotten explanation. When the rational grammar of a wall becomes illegible, when the how of its construction slips from living memory, the human mind instinctively fills the silence with story. The very stones that were once a testament to meticulous engineering become, to later eyes, artifacts of magic or the divine. The colossal, rough-hewn blocks of Mycenae were so incomprehensible to the later Greeks that they could only be the work of a race of one-eyed giants from their oldest legends. It was a logical conclusion if you lacked the vocabulary of gravity packing and patient quarrying. Across the Mediterranean, the titanic foundation stones of the Baalbek Terrace, some weighing hundreds of tons, spawned their own legends. Medieval Arab traditions attributed them to a race of pre-flood supermen or to the biblical king Nimrod, a figure of mythic prowess. The stories were a cultural translation, an attempt to narrativize a technological feat that seemed to defy every known law of human limitation. Perhaps the most poetic of these translations comes from the Andes. Spanish chroniclers, gazing upon the seamless joints of Inca masonry, recorded a local belief that the builders possessed a mysterious plant or liquid that could soften stone like clay, allowing them to mold the blocks into perfect fits before the material hardened again. This myth of softening stone is a beautiful, almost alchemical metaphor for the actual process. It captures the essence of the stonemason's art, the slow, patient reduction of a hard surface through abrasion and iteration, making the stone appear to yield willingly. The myth understood the effect, the seamless result, but had lost the method, the thousands of hours of scribing and grinding. In every case, the pattern is the same. A structure stands that common knowledge says should not exist. Without the engineering lexicon to explain it, the only remaining grammar is that of the supernatural. The master mason is transfigured, becoming either a monster, a demigod, or a wielder of lost arcane secrets. Their humanity is erased by the very permanence of their achievement. Reclaiming the rational explanation for these walls does not strip them of wonder, it redirects that awe to its proper source, human ingenuity. To understand that the Cyclopean wall is a brilliant application of friction and mass, that the Baalbek stones were moved with levers, ramps, and orchestrated labor, and that the Inca joints were born from relentless trial and error, is to see the true miracle. It is the miracle of persistent observation, of collective problem-solving, and of knowledge passed hand to hand across generations. The myths were a tribute to the scale of the accomplishment, but the engineering reality is a tribute to the profound capabilities of the human mind and spirit. This reclaimed respect is no longer a passive admiration for the mysterious past. It is now an active force, inspiring a modern movement that looks to these ancient texts not just as artifacts to preserve, but as a living library of solutions for our own turbulent future. The ancient grammar of stone is not a relic, but a living blueprint for our future. In an era of climate crisis and resource constraints, architects and engineers are returning to these old texts, not for nostalgia, but for survival. They are discovering that the principles of dry stack construction, local material sourcing, and passive seismic design form a powerful manifesto for sustainable building. This emerging field, known as applied, treats our oldest walls as a repository of low-tech, high-intelligence solutions. The logic is compelling. A wall built without cement eliminates the massive carbon footprint of that industry entirely. Using stone from the building site itself slashes transportation emissions to zero. And those intricate, interlocking joints designed to dance with earthquakes offer a model of resilience without complex, energy-hungry technology. This is not about abandoning modern tools, but about redirecting them. Imagine a contemporary stonemason using a digital scanner to map a quarry face, then employing a computer-guided saw to extract blocks with the same geometric intelligence as an Inca master, but with far less waste. This fusion is what some call Vernacular 2.0, taking the deep place-based wisdom of ancient techniques and augmenting it with precision machinery to create structures that are both hyper-local and globally relevant. It represents a profound dialogue across, where the question is no longer how did they build that, but what can their building teach us about constructing a durable, graceful world today. To fully grasp the genius of this ancient language, however, we must also learn to read its wounds, to understand what happens when this carefully crafted dialogue with physics is interrupted. A fracture in a wall is a sentence left unfinished. These imperfections, the cracks and collapses we often see as signs of decay, are actually some of the most eloquent parts of the engineering language. They are grammatical errors that reveal the underlying rules of the syntax, a forensic record of a conversation between human design and the relentless forces of nature. When a diagonal fissure tears upward from the corner of a window or doorway in an ancient ruin, it is not random. It is a clear statement about stress concentration. The builders understood that sharp, 90-degree angles were natural focal points for pressure, which is why so many cultures evolved the trapezoidal shape. A crack originating there is the structure telling us, centuries later, where its designers may have miscalculated the load, or where an unforeseen settlement in the foundation redirected forces to a vulnerable point. Similarly, look at the face of a stone block that has begun to flake away, a process called spalling. This is a materials testimony against water. Over hundreds of winters, moisture seeps into a microscopic flaw in the joint, freezes, expands, and slowly pries the stone apart from within. This failure mode reveals where the perfect seal of a joint was compromised, or where a particular stone, despite the builder's best assessment, contained a hidden weakness in its grain. It speaks to the long-term environmental dialogue the wall was forced to endure, a dialogue of frost and thaw that even the most precise masonry could eventually lose. Perhaps the most telling failure of all is the partial collapse. Across countless ruins, you will see that the upper sections of a wall have often tumbled down, while the battered base, wider and more stable, remains defiantly intact. This is not a failure of the entire language, but a vivid illustration of its core principle in action. The batter, that deliberate inward slope, ensured the center of gravity was so deeply anchored that even when the top was shaken loose by an earthquake or undermined by root growth, the foundation refused to topple. The base held its ground, a stubborn declarative statement about the correctness of its original angle. By reading these cracks and collapses with a forensic eye, modern engineers can perform a kind of engineering. They can reverse engineer the assumptions of the original builders. They can calculate the wind loads a Mycenaean fortress was designed to withstand, or map the seismic frequency of tremors that an Inca wall was tuned to absorb, based on the specific way its stones finally yielded. Each ruin becomes a historical document, a slow-motion recording of a battle. And in the overwhelming majority of cases, what we are witnessing is not a defeat. We are seeing a design that held firm for 2,000 years before a single crack appeared, or a wall that lost its upper stories but whose base is still perfectly level and true after 30 centuries. That is the ultimate test of this language's efficacy. Its sentences were written not for decades, but for geologic time. They were composed with the understanding that true success is measured not by never failing, but by failing gracefully, revealing your secrets only after an eternity of steadfast service. This leads us to a final, unifying thought. If we can now read the grammar, understand the mathematics, and even learn from the failures, what is the core philosophy that binds all these global dialects together? What is the one sentence that every ancient wall, from every continent, is ultimately trying to speak? 4,000 years of silence is the most profound review a structure can receive. The ultimate validation of this ancient engineering language is not found in a textbook, but in the quiet persistence of a wall that has witnessed the rise and fall of civilizations. To endure for 40 centuries is to pass the most rigorous, unrelenting quality assurance test imaginable, a trial conducted by wind, water, freeze, thaw, and the slow creep of the earth itself. The walls that speak to us today are the ones that mastered a specific dialect of foresight, a grammar of permanence written in response to time's specific threats. The first word in that dialect is material selection. Builders consistently sought out stone with low porosity, dense crystalline structures like granite, basalt, and some limestones. These materials absorbed minimal water, resisting the insidious cycle of freeze-thaw spalling that could turn a solid block to rubble over centuries. But choosing the right stone was only the beginning. The design itself had to become a partner in preservation. Every element was shaped to shed water, not trap it. You will notice that the tops of surviving walls are rarely flat, they slope, or they are capped with larger protective stones that direct rainfall away from the vulnerable joints below. The meticulous fitting of those joints served another long-term purpose, accommodating thermal expansion and contraction. As stone heats in the sun and cools at night, it minutely swells and shrinks. A rigid, mortared joint would crack under this constant, gentle pressure. But a dry stone joint with a perfect fit allows for this microscopic movement, letting the stones breathe with the daily cycle of temperature without fracturing. Perhaps the most critical, and often invisible, factor is the conversation with the ground. A flawless wall built on unstable soil is a sentence destined to crumble. Ancient engineers displayed a deep understanding of geotechnics, often excavating down to bedrock or creating layered, compacted foundations that would distribute the structure's weight evenly and prevent differential settlement, the uneven sinking that tears even the strongest masonry apart. This comprehensive approach reveals a stark truth about one common weakness: early mortar. In many cultures, the first attempts at using lime or clay-based mortars created a fatal vulnerability. These binders often decayed far faster than the stone itself, washing away and leaving gaps that allowed water in and undermined stability. The most enduring walls often come from traditions that avoided this trap altogether, or used mortar so sparingly it was not a structural crutch, but a gentle filler. This longevity was never an accident. It was the direct result of empirical knowledge encoded into the language, a slow accumulation of wisdom gained by observing which walls stood and which fell over generations. A builder learned from the collapse of his grandfather's project, and his grandson would refine the technique further. It was a continuous, centuries-long experiment, with each surviving wall serving as a published paper in the world's oldest engineering journal. This legacy of resilience, this hard-won dialogue with eternity, now faces a new and relentless force, one that does not test with the patience of glaciers, but with the immediate pressure of our modern world. Our ancestors built for, but they never faced a world of vibrating concrete and acidic skies. The very atmosphere that once only weathered stone with patient rain now carries a chemical edge, a slow dissolution from industrial pollution that etches away the crisp details of carved glyphs and the sharp lines of perfect joints. This is not the gentle dialogue of frost and thaw, but a corrosive monologue. Ground vibrations from nearby highways and railways transmit tiny, relentless tremors through the soil, a constant background hum that can gradually unsettle foundations laid for stillness. Even the roots of a seemingly harmless plant, seeking moisture in a minute crack, can become a silent, prying lever over decades, patiently performing the work an earthquake might do in seconds. Yet perhaps the most intimate modern force is the touch of admiration itself. The cumulative effect of millions of footsteps, of hands resting on the same polished surface for a photograph, creates a wear pattern that no ancient builder could have anticipated. The stone language, designed to speak across ages, now risks being whispered away by the breath of its own global audience. This new assault demands a new kind of literacy, one of conservation. Modern stewards of these sites are writing a contemporary chapter in the ancient text, using tools and materials unknown to the original authors. Their work is a profound ethical exercise in translation. They employ invasive grout, designed to be chemically softer than the original stone, to fill cracks and stabilize joints without creating a hard, damaging point of stress. They install nearly invisible subsurface drainage systems to divert groundwater away from fragile foundations, mimicking the natural water-shedding principles of the original design with plastic pipes and gravel beds. The goal is never to restore a wall to some imagined, perfect original state, but to stabilize its current sentence, to protect its authenticity from further loss. It is a practice of minimal intervention, where every action must be reversible, and every modern addition must be distinguishable from the ancient work to the trained eye. The conservator's mantra is to support without rewriting, to let the original grammar speak for itself, even if its voice is now fainter and more fragile. This delicate balancing act between preservation and access defines our role as curators of this shared heritage. We are no longer passive decoders of a silent language. We are its active guardians. The challenge is to manage the flow of visitors in a way that protects the physical fabric while still allowing the emotional and intellectual impact of the site to resonate. This might mean constructing viewing platforms that keep feet off ancient floors, or using subtle lighting that reveals detail without generating damaging heat. It requires a deep collaboration between archaeologists, structural engineers, tourism specialists, and the local communities for whom these walls are not just history, but living identity. The question we face is not merely how to keep the stones from falling, but how to preserve the meaning they hold, the awe they inspire, and the silent conversation they began thousands of years ago. This earthly stewardship, however, is already pointing our gaze toward a far more alien horizon. If this language of rock and balance could create enduring habitats on a dynamic, living planet, might its grammar hold the first principles for building shelters on a world with no atmosphere at all? The final frontier may be written in the world's oldest language. On the Moon or Mars, the cost of transporting a single bag of cement from Earth would be astronomical, a fundamental economic equation that forces us back to first principles. The solution being seriously studied by space agencies is not futuristic polymers, but a direct translation of ancient wisdom, building with what is already there. On the Moon, that material is regolith, a fine, abrasive dust. On Mars, it is basalt rock, a volcanic stone familiar to builders from Mycenae to Easter Island. The proposal is to use focused solar energy, or microwaves, to sinter this local material, essentially fusing the dust into solid, interlocking blocks, or to cast it into shapes using a binding agent derived from the Martian soil itself. The resulting structures would not rely on imported steel or complex machinery, but on the timeless grammar of compression and gravity, a language perfectly suited for environments with only a fraction of Earth's pull. The European Space Agency's conceptual regolith printer is, in essence, an attempt to automate the patient work of an Inca stonemason, using lasers instead of stone hammers to articulate blocks that fit together with perfect, load-bearing joints. This vision creates a stunning continuity. The first permanent human habitats on another world may consciously echo the seismic walls of Peru or the corbelled vaults of the Mediterranean. It suggests that the ultimate test of this engineering language is not merely enduring on Earth, but providing a blueprint for survival on alien shores. The silent conversation between human ingenuity and raw material, a dialogue begun at the dawn of civilization, could become the foundational syntax for an interplanetary future. This forward-looking vision, however, circles us back to a deeply human truth, one etched not in the grand scale of empires or space exploration, but in the intimate personal mark of a single craftsman's hand. A perfect joint is also a signature. Look closely at the face of some ancient stones, and you may find faint, deliberate marks, a simple cross, a series of notches, a unique symbol. These are not random scratches, but the personal glyphs of the masons who shaped them. They were a way for an individual to say, "I was here. My hands did this." In a project spanning decades and involving thousands, this small act of claiming ownership reveals a profound psychological truth. The builders were not anonymous cogs in a machine. They were authors, inscribing their identity into a story meant to last forever. This human impulse transforms the entire endeavor from mere construction into an act of communion. The backbreaking labor of moving a 70-ton block was not just a logistical puzzle. It was a shared trial that forged community bonds. Historians suggest that the rhythmic chants used to coordinate pulling teams, the communal meals provided by the state, and the celebratory festivals held when a major phase was completed all served a vital social function. They turned exhausting work into a collective ritual, a shared narrative of achievement where every participant, from the quarryman to the water carrier, could feel they were contributing to something immortal. The wall itself became a physical manifestation of that shared memory and identity. It was a covenant in stone, a silent promise whispered from one generation to the next. It said, "We were here, we endured, and we built this for you." In a world where life was often short and uncertain, these structures offered a powerful psychological anchor, a declaration of continuity against the fragility of existence. They answered a deep, universal human anxiety about being forgotten. To stand at the base of such a wall was to feel connected to a lineage, to be part of a story much larger than oneself. This emotional dimension completes our translation of the engineering language. The perfect geometry was an act of love for precision. The seismic joint was an act of care for future generations who would live within its protection. The choice of enduring stone was an act of hope, a belief that the community and its values were worthy of permanence. When we decipher the secrets of stone, we are not just uncovering ancient physics, we are listening to the oldest parts of ourselves, our need to create, to collaborate, and to reach across time with a message. It is a language of legacy, written by calloused hands for eyes they would never see. Having listened to this language in all its dimensions, physical, mathematical, and profoundly human, we can now attempt to articulate its core grammar, to write down the fundamental rules of this silent, global conversation. 6 simple rules whispered from 1,000 silent walls. This is the distilled syntax, the core grammar of the ancient engineering language. The first tenet is a dialogue with forces. The builders did not see gravity, seismic energy, or climate as enemies to be conquered, but as partners in a permanent conversation. They leaned their walls inward to let gravity lock the stones. They designed joints to sway with an earthquake's energy, not shatter against it. They shaped surfaces to shed water and withstand freeze and thaw. This was not defiance, but a profound collaboration with the natural world. The second principle is material collaboration. A master builder was a listener. He learned the story written in a stone's grain, its cleavage planes, and its resonant sound. He selected granite for foundations that needed to bear crushing weight, and softer limestone for carvings that told stories. By persuading stone with fire and water, letting its own properties guide the fracture. The material was not a passive substance, but an active participant in the work. Third is geometric order. Behind every seemingly irregular form was a hidden framework of mathematics. They used the golden ratio for harmonic proportion, Pythagorean triples to ensure perfect right angles, and celestial alignments to anchor buildings to the cosmos. This geometry was their universal design software, a repeatable, scalable system that allowed a single architectural idea to grow from a small shrine to a mountain city. It was the invisible grid that gave chaos a coherent shape. Fourth is joint intelligence. The space between stones is where the language finds its eloquent voice. The goal was never just to fill a gap, but to create a complex interface that maximized friction and distributed load. The polygonal joints of the Andes, with their 12-angled faces, transformed a wall into a 3-dimensional network. A force on one stone was shared by all its neighbors, creating resilience through interconnectedness. The perfect fit was a functional imperative, a way to make many stones behave as one. Fifth is logistical choreography. Before a wall could speak of physics, its words had to be moved into place. Transporting an 800-ton block or feeding an army of workers was a masterpiece of social organization. It involved sledges on lubricated tracks, earthen ramps that turned vertical lifts into horizontal pulls, and rhythmic chants that synchronized the pull of 100 people. This was the syntax of collective action, proving that the most permanent structures are built on foundations of meticulous planning and shared effort. Finally, the sixth tenet is semantic intent. Every technical choice carried a cultural meaning. A Cyclopean wall of jagged boulders shouted a message of intimidation and raw power. A seamless Inca joint whispered of harmony with the living earth. A trapezoidal doorway aligned with the solstice sun embedded cosmic order into daily life. The engineering was never just about how to build, but about what the building was meant to say about the gods, the king, or the community itself. Together, these 6 principles form a coherent philosophy. It is a worldview that prioritized resilience over speed, sustainability over convenience, and meaning over mere monument. It asked not what is fastest to build, but what will last the longest and speak the deepest truth. In an age facing resource limits and climate instability, this ancient language is no longer a relic. It is a profound and urgent question posed to our modern world. What would happen if we chose to build by this old grammar once more? That universal language of stone was humanity's first great book of knowledge. We began this journey seeing ancient walls as silent ruins, and we leave it seeing them as one of our species' most eloquent and enduring achievements. The secrets we have uncovered are not about lost super technology or mythical giants, but about a profound and universal grammar of engineering. It is a grammar of gravity, a vocabulary of joints, and a poetry of permanence, spoken in distinct dialects by cultures separated by oceans, and to decipher this language is to gain far more than historical insight. It is to recover a vital toolkit of sustainable, resilient design. These principles of local materials, passive seismic resilience, and intelligent geometry are not relics. They are urgent blueprints for a world facing resource limits and a changing climate. These silent walls challenge our most basic assumptions of linear progress. They remind us that advanced knowledge is not always about adding complexity, but often about deepening our observation and working in harmony with fundamental forces. The true measure of their genius is found in the quiet fact of their persistence, a 4,000-year review that most modern structures will never face. So the next time you find yourself standing before an ancient stone wall, in person or even in an image, pause for a moment. Look past the surface of weathered rock. See the deliberate batter, the intricate puzzle of the joints, the silent conversation with the earth. Listen closely. You might just hear the whispers of the master masons speaking across the. Their lesson, carved in granite and limestone, is clear and timeless. To build a durable future, we must first remember how to speak the profound wisdom of the past. If this journey into the language of stone resonated with you, please give this video a like to let us know. Subscribe for more explorations into the mysteries woven through our history. And we would love to hear from you in the comments below, which ancient structure speaks most powerfully to you and what you believe it is trying to say.